Okay, students, coming to the gravitation, another topic. Newton's law of gravitation from planetary motion. Newton's law of gravitation from planetary motion. So we know that there are eight planets. This is the sun, planets. We know that our solar system is the sun. Around the sun, these planets are rotating in circular motion. So the first one is Mercury, the second one is Venus, the third one is our planet Earth, next one is Mars, and so on. You see that we can this G value is also by using that Newton's formula. We can find out these forces between sun and any planet, any planet by using that F equal to G into mass of the sun into mass of the another planet divided by the distance between those two sun and another planet. Here you see that, let us assume you see that here the planets of our solar system revolve around the sun. These planets, all planets are rotating around the sun. So this Mercury, to complete one revolution, it takes 88 days. Earth, we know that to complete one revolution around the sun, it takes 365 days. Mars, it takes 687 days. So here the Kepler proposed relation between the time to complete one revolution any planet on his circular path. Let us say that you take Earth, you to complete one revolution, the time is called let us say that t time. Obviously from here to here, that is the radius. You can understand. Here I have separately developed a diagram. Here is the sun. Let us say that one planet, that planet is rotating in this circular path. Obviously we know that already before discussions, this is the velocity. So therefore the Kepler proposed the relation between the time and the radius. The time in the sense to complete one revolution, that is called t time. This is the radius from here to sun to that planet. This distance is radius, center to this center to sun and center of this planet, radius. This is a radius. This is the rotating in this path. What he proposed that relation, the t1 square, let us say that t1 square, or otherwise you can take it here another planet, another path. This is the another planet. This planet is t1, this planet is t2 to complete one revolution. This is the R2, this is the R1. Let us. So from this he proposed the relation between the time revolution to complete one revolution, let us say t, and radius t1 square. Suppose this is the one planet to complete one revolution, and this radius, the relation is t1 square. Suppose that planet is completing t1 square time, the radius is required cube of that radius. So therefore there are two planets, you can take that relation because all these planets rotating about the sun. Before discussions, any two particles, they are attracting to each other. Whatever force is there, already we discussed here. Whatever force is there, the same force is exerted from this object. This object is exerted same force on this. This object is exerted the same force on this. So this is the radius. The same on that principle, on that concept. By using that concept, and the Kepler is also proposed this relation. We have to understand here T1. So by using that this concept, the Kepler proposed T1 square divided by T2 square equal to T1 cube R1 cube divided by R2 cube. So the time is if the one planet time becomes T square, automatically the radius becomes the proportional radius becomes cube. Another planet with respect to sun, so it takes T2 to complete one revolution. The time T square obviously R2 becomes R cube. So therefore he has given this relation. He has given this relation. Proposed the relation between time and radius between the two planets. Of course, you can take it sun to Mercury or sun to Venus or sun to Earth. So therefore, this the relation is established. So therefore, we know that force equal to mass into in circular path. Force equal to mass into v square by r. V equal to 2 pi r by t. We know that. You see here. Suppose this is the planet. To complete this is the complete one revolution. The circular revolution. That form like 2 pi r. The distance equal from here to here, the distance equal to, we know that formula 2 pi r. To complete that distance, the time required t. So therefore, velocity equal to distance by time. Displacement between the distance by time, velocity equal to distance by time. So that this is equal to 2 pi r divided by t. 2 pi r divided by t. So that F equal to mass into v square by r. In V you substitute 2 pi r by t. So therefore mass into 2 pi r by t whole square divided by r. So if you simplify this one, mass into m into 4 pi r square pi square r square divided by t square into r. If you simplify this one, if you rearrange this one, if you simplify this one, you can get cancelled. R and R square get cancelled, so that equation becomes F equal to 4 into pi square m into R divided by t square. This is the force we can find out by using this equation. Now we can see the between the two planets. We can calculate the force. So Kepler proposed the relation between the time to complete one revolution between the radius. He has given T1 square one planet. It takes time T1 square. Automatically the proportional radius is cube of that radius. The two planets. There is a, because these are the relative. Sun around that these are planets are rotating. So therefore we can establish this relation is established by Kepler. Okay, so if you consider here two planets A and B, let us say you take this diagram, A and B, this is the one planet, this is the another planet, A and B, this mass equal to, let us say that M1, this mass equal to M2, the radius, this radius equal to R2, this radius equal to R1. Obviously we know that before discussions the force is exerting on sun, and sun is exerting on this planet. At the same time the force is exerting on this planet B. The B is also exerting the same force on the sun. So this planet, let us say that F1, this planet, this is the, let us say that F2. So from this F1 equal to we are already simplified. F1 equal to 4 pi r square m1 r1 divided by t1 square. At the same time another planet F2 equal to 4 pi r square m2 r square divided by T2 square. Here, so you take that two relative, because the planets are rotating about the sun. So that according to this Kepler, so that F1 by F2 equal to m1 r1 t square divided by m2 r2 t1 square. If you substitute and substitute in these terms, you can get this relation. This this form. Suppose you see here, this is the rearranged this equation is right. Another form, f1 by f2 equal to m1 r1 divided by m2 r2 into r2 divided by r3 whole cube. So how this is substituted here? You see here, t2 divided by t1 whole square. There is a relation here, t1 by t2, t square, t1 square by t2 square equal to r1 cube divided by r2 cube. In t1 divided by t1 divided by t1 whole square equal to r1 divided by r2 whole cube. In this place, t1 divided by t2, I substitute r1 divided by r2. Here t2 by t1, so that it is also r2 by r1 whole cube. So this is the this equation is written in this form. T2 divided by T1 whole square replaced with R2 divided by R3. Sorry, R1 whole cube. So this is the equation, F1 by F2 equal to M1 R1 divided by R1 M2 R2 into R2 divided by R1 whole cube. If you simplify this one, it gets square and it gets square. So I have rearranged here this equation. F1 divided by F2 equal to M1 R2 square divided by M2 R1 square. If you rearrange this equation, M1 divided by R1 square divided by M2 divided by R2 square. From this equation, we can understand that if you take any one, F1 divided by M1 R1 square, R1 square, so F1 is directly proportional to the M1, F is inversely proportional to the 1 by R1 square, R1 square. So therefore, I would like to write this equation. Therefore, F is proportional to the mass divided by mass of that planets divided by r square. So this I have to arrive. F is directly proportional to m divided by r square, which is already proposed by the Newton. F is proportional to the mass by r square. So the force, in this planet system, the force exerted on a planet by the sun is proportional to its mass as well as 1 by r square. That we have learned by Newton's third law. We know that action equal to reaction. The force is proportional to the mass of the planet. It should be proportional to the mass of sun. Let us say that m. So therefore, in between the sun and the another any planet, we can establish that relation. F is proportional to the mass of the sun divided by mass of any planet divided by the distance between that sun and the planet, r square. Okay, so therefore this equation is rearranged. F equal to G, constant of gravitation into mass of the sun into mass of the planet divided by r square. Like this, we can calculate between any two planets force and force. We can calculate any two planets between the force. From this equation, you can calculate. If you know these G value is constant, so therefore, if you want to calculate the F, if you know the mass of the sun, if you know the mass of the planet, another planet, you know the distance between the two things, r square, you can calculate the force. Or otherwise, if you want to calculate the any object, any planet, another planet mass, if you know we know the gravitational constant value, you know the sun value, if you know that that planet or distance, you can if you know that force, the total force, you can calculate the mass. Like this, from this you can establish, derive so many equations. So let us say that for example, so from this equation, if you want to find out any object, one planet is there, let us say that is the m. So you rearrange this equation, this equation, f into r square root divided by g into m. You can find out the mass of that planet. If you know that plan of the planet, if you this is the force, if you know the force, you know the distance between that sun and the that particular planet. This is the g value. We know that. You know the mass of the sun. You can calculate the mass of that planet. Like this, you can get different equations. So whatever the term is required, you can take out and we can calculate from this equation. This is about the Newton's law of gravitation from the planetary motion.